So we're going to kick off this afternoon with Mark Olin from Mentor Graphics. Mark is a functional verification specialist. We have a very close collaboration with Mentor. Mentor supports our DV Club as well as our verification futures. And just as an advert for our next DV Club is on April the 8th. It's held in the UK, or it's held in Europe. It's actually held in UK, in Bristol and Cambridge, and in France and in Germany and in the Netherlands as well. But there is remote access, and the reason I'm saying this is because our next DV Club will be delivered by Harry Foster, who's chief scientist of Mentor and verification. This morning, Mentor do a survey, and Harry Foster runs that survey. It's done independently by an independent company called Wilson Research, and Harry's presentation will be on the findings from that research, so you'll be able to see how many. We had a presentation from the Synopsys this morning about SoC verification. Well, I know in Harry's statistics, in Harry's research, the statistics about how many chips now are SoC chips, the number of companies using OVM, UVM, SpecMan, the number of companies who adopted SystemVerilog, the average number of verification engineers versus design engineers, and I know Harry says that's sort of becoming one-to-one now. So we were at a company yesterday who have a ratio, I think they have 6 verification engineers to 15 design engineers, and they said, no, they know this, they're going to go back to their management and say that the we're 2-to-1 or 2.5-to-1 still. So those statistics can be very, very useful, and also you can look at the adoption and the trends within our industry. That's on April the 8th. Harry will be speaking from the UK, but it does get broadcast. This morning we have over 50 people online listening to this presentation. So, and it's a short 1-hour presentation from Harry. So if you're interested in statistics, that would be useful. But staying with Mentor Graphics, today we have Mark Olin, who is, as I say, a functional verification specialist at Mentor Graphics. He spent 30 years in semiconductor design, verification, and manufacturing test, and has authored papers in the areas of intelligent testbench automation, design for test technology, semiconductor manufacturing test automation. He wrote his first testbench in 1981 at Raytheon. Wow, this is amazing. And went on to spend 10 years working at Teradine in the ATE and the DFT industries. He became vice president of Cascade Microtech's thin film wafer probe division before co-founding Lighthouse Design Automation, where graph-based intelligent test bench automation was first successfully applied to semiconductor design verification. Mark graduated from MIT, which is very impressive, with a BS in EE and CS. I'm going to hand it over to Mark. Thank you.
Thanks, Mike, very much. Thanks, everybody, for inviting me to speak today. I am going to give you a little bit of a sneak preview of some of Harry's slides, but as Mike said, the best way to actually see all of them is to attend the session in April, it is, you said, when he'll go through and show you more about that. So as the slide shows up here, my title is Verification Entrepreneur, which often causes a lot of questions. So how many people, by show of hands, know what entrepreneur is? You know what an entrepreneur is, right? So I'm like an entrepreneur. I'm always looking for good technology in the area of verification on behalf of Mentor Graphics. But I'm interested in technology not only for technology's sake, like a good entrepreneur would be, but I'm also interested in how it provides value, what the return on investment is. So hopefully I can show you some of those things here in the presentation. I'm going to move along pretty fast. So four parts that I'd like to cover. I'd like to give you a little bit of a preview of some of Harry's slides from the worldwide study, talk about macro trends in verification and verification enablers, discuss some of the new technology that's being developed by Mentor, as well as leave you with some alternatives of where you can go to find more information. So, as Mike said, Mentor commissions a study. It's conducted by Wilson Research Group. That's about all we do. Mentor pays for it. We commission it. They do the rest. We stay away. As you can see down at the bottom, there's no identification that it's Mentor holding the study. We have polled over 500 different customers. We analyze the data and see that the number of responses tracks very closely to the actual market share usage of all of the EDA tools. So this is a very broad-based survey, and it's also global. So some of you out there in the audience here or on the phone may actually have answered the survey, so you may recognize some of these. So this is good news for us and good news for TVS. As Mike was saying earlier, that what we're seeing in the survey is that the number of verification engineers has nearly caught up with the number of designers. This is according to the survey. You can see that over the past 5 years, we've seen 4% and 5% growth in design engineering, and we've seen almost a doubling in size, 58% over a 3-year period and 11% in verification engineers. So, but this is only the tip of the iceberg. This is only the beginning, because in addition to that, the survey also asked designers, how much time do they spend designing versus how much time do they spend verifying? And an interesting thing occurred in 2012, that designers told the survey that they spend more than 50% of their time verifying. So indeed, the amount of verification investment is continuing to skyrocket, and it's demonstrated not only by the increasing number of verification engineers, but the increasing amount of time that designers are spending doing verification. If you look at this chart, this shows over the 5-year period the trends of overall investment in verification compared to design. You can see here the red arrow on the left shows here going as we go from light blue 5 years ago to dark blue. Everything to the left-hand side of 50% is dropping. So we're seeing less and less customers that are spending less time in verification. Over on the right-hand side, more and more customers are spending more than 50% of their time in verification. Now, this is the one slide that I'll show you that does not come from the survey data. Okay, this comes from a different piece of data, which is the Design Automation Conference press releases, and this shows, once again, relative trends of design versus verification. What you can see here is that over the past several years, attendance at the Design Automation Conference has been declining. So Mike, what this means for you here is that this shows our estimated growth opportunity of the TVS market opportunity in the Verification Futures Conference as more and more effort or energy is put around verification. So thanks for leading this effort and giving us a forum so we can exchange ideas and technology. So while we're on the topic of Verification Futures Conference, so you did your analysis of last year's event in November across the 3 sites in Europe. We did ours as well, although we got it on one slide. So this shows 8 of the customers that presented their top 3 challenges, and not surprising, each one of them identified performance was one of their top concerns. So there's always a need to go faster and always a need to do more. But what we also learned was that they also had a range of other things that were very concerning to them, that were challenging to them, that did indeed range from debug, we heard that earlier today, to coverage, to low power, we also heard that, hardware, software verification, verification IP, and reuse. So the overall challenges are broadening. The other thing I think we learned from this is that this was supposed to be identifying the top 3 challenges, right? So it looks like in each one of these cases, the presenters had a really hard time staying to just 3 challenges in verification. So, okay, so back to our survey. So indeed, one of the things that we've seen in terms of the trends over the past 5 years, one thing hasn't changed. Very little difference between these curves on the graph. And that's how many designs finish on time versus how many finish behind schedule. So 2/3 of all designs, according to the respondents, finish late, and as Harry likes to say, the other 1/3 of all respondents lie. So So we're here to help those 1/3 of the respondents and see what we can do to help them not have to lie anymore when we look at their challenges. So we also heard earlier today, and I think you're going to hear some consistencies between the presentations, that it is an SoC world. Again, out of Harry's presentation, if you look at the trends, the number of embedded processors designs with none has dropped from 48% down to 22%. So 78% of all new designs have at least one embedded processor. And notice the two red arrows in the middle and on the right show that the number of designs with multiple processors has been increasing over time. And as you might imagine, over the period of time, we've also seen the average number of processors per design grow by a factor of 2, from 1 to slightly over 2. Now, before you say, oh, but this is all ASIC-based designs, FPGA designers were included in the survey as well. And what this shows is that even in the FPGA world, only 45% or 44% of designs have no processor. So 56% have at least one. Now, certainly in the FPGA world, there are far fewer multi-core processor designs. But you know what? That's going to be changing too with some of the things that we're seeing coming out of companies like Xilinx and Altera moving forward. So even in this case, it is still an SoC world in the FPGA world as well. So what kinds of trends and what kinds of analysis can we draw from some of these? So let's look and see if we can identify 3 major trends that we're seeing. So one trend, again, we saw this earlier today, is that SystemVerilog growth has just been skyrocketing. Over the past several years, it's the, other than perhaps C, C++, which I think you'll hear a little bit about later today as well, it's the verification language that has been growing, while all of the others are flat at best or even tailing off. SystemVerilog is not limited to only large designs, although certainly almost 90% of customers are using it for larger designs. But you know, even down here with the smaller designs, we're seeing 60% of customers have moved to SystemVerilog. Likewise, the base class libraries, the decision has pretty much been made as well. The growth in UVM has been enormous, while most of the others are either dropping or perhaps staying flat to support legacy designs. So the standards have been emerging, but that's not enough. The second macro trend that we're seeing is that we are starting to move from a well-defined process and verification for IP and IP blocks to a well-defined process for SoC, including and starting with unit level verification, connectivity, integration, and system level. So here's what we mean by this. If we look at sort of a trivialized picture of a SoC, we're pretty common with the concept of block level verification, achieving coverage as fast as we can, sort of a test under all conditions, interface-centric technology. So we verify each one of these processors. But turns out that there's actually a very interesting subsystem that is sometimes boring, the interconnect, but it's a very complicated and increasingly so complicated subsystem in your SoC designs. Thousands of connections to check, and it's more than just point-to-point verification. Third step is verifying your data path, your registers, your memory map, and some of the basic power control. We happen to agree in low power verification. If equal, if not more, benefit by verifying your software's low power efficiency as well as the hardware. And then finally, the full system level application software, run your software against your hardware, verify the entire design. And what we're trying to do is to follow this process so that we can avoid this problem. And how many times have you heard this? The hardware works, the software works, but the system doesn't work. So that's the challenge that we're trying to avoid here. So the paradox is that you really don't want to start with the tools. Because if you start with the tools and the technology, which is what we're all here to talk about today, and then develop ad hoc processes, what surveys actually show is that it actually results in a cost increase. Conversely, if you start with a process, you put together a good, rigorous verification process, and then adopt tools to fit within that process, cost savings. So let's see what we mean by that. So with unit level verification, some of the traditional test techniques used include directed tests, constrained random tests, graph-based techniques, which we'll talk about in a little bit, lots of verification IP, coverage techniques, assertions, formal when possible. And what we're actually seeing now is that, again, according to the survey, more and more of these technologies are actually being adopted. More code coverage over the past 5 years, more assertions, more functional coverage, and more test-bench automation. Connectivity, again, we mentioned it's not just simply point-to-point. You've got very complex bus fabrics, cascaded, hierarchical, with lots of constraints and dependencies between masters and slaves. So it's a whole lot of a different challenge now than it used to be. And then verifying, again, the IP integration, data path between your processors and your memories, registers, control, clock domain crossings, verifying all of that before we move to the system level. Now, I'll give you a little bit of a sneak preview here with this slide. This is something that we're working on in that entrepreneurial area of new technology, where we're developing new verification IP in the area of cache coherent interconnect. So this is where we can verify not only protocol checking, which is something that you're used to using today, but be able to verify cache coherency, performance analysis, including bandwidth and latency, as well as visualization for debugging, coverage analysis to verify that we're covering the entire specification, and verifying all of the legal combinations at the transaction level across our cache coherent interconnect. So this is something where Mentor is investing in heavily today, and this includes both in the simulation and emulation environment, creating consistent verification IP so that we can move seamlessly from one environment to the next. And then finally at the system level, where now we're going to be verifying the full functional interaction, not only between multiple blocks, but between the firmware, the middleware, the hardware, the software, the whole thing. It requires all IP at this point to be integrated, and this brings up lots of other challenges as well. So in this area, in the full system level verification, here's a challenge that we're seeing in the market today. What people typically start to do with that SoC is they'll write some directed tests in C. We did see in the survey that there is some slight growth in use of C or C++ in Testbench and in verification languages. The challenge is that writing tests in this mode are very challenging. We might be able to write a hello world or a dry stone test, a little bit of a performance, but we run into challenges because it's very difficult. So where am I going to find another C or assembly level test bench that I can run against my hardware? And what I can do is look at my own software, my operating system, my drivers, and even the application software. But of course, as we saw earlier, now we're firmly moving into the emulation platform, perhaps even beyond that into hardware prototyping. Now we're running billions and billions of cycles, and our challenge now is how are we going to, for one, how are we going to run all of them in simulation at speed with the right accuracy, with the right level of diagnostics so that we can actually debug these problems. It's very challenging. So one of the things that we're working on with the graph-based technology is bridging the gap in the middle and using the graph to automatically synthesize C-test programs that can be loaded into your embedded processor's memory and executed. And if done properly, this will enable you to create a breadth-first C-test environment as opposed to on the right-hand side where we have a depth-first verification environment where we can test all different kinds of modes, commands, connections, interfaces, combinations of things of your entire SoC. So here's how this works. will continue to use the graph as a sequence generator or scenario generator to drive your verification IP at the SystemVerilog level for RTL. But now we're also going to use a graph to drive the C-test program generation to create reusable tests that are executed by the processor. So you could think of it as outside-in testing or inside-out testing. So macro trend number 3, what gets measured, gets done, gets improved, and gets managed. So the other thing we're seeing is coverage and power across the entire verification spectrum. Now, in terms of functional coverage, we talked about, someone was asking, is there a way to increase your coverage and find your holes faster? And the answer here is yes, there is. There are ways to do that, and the graph technology is able to do that in the functional area. In the code coverage area, let's look at this in a little more detail. In the code coverage area, the coverage is reasonably explicit. So we're able to use formal technologies to observe or investigate the design and the test bench and to be able to give feedback as well. The challenge is in the middle here in the assertion area when you're looking for deeply embedded or implementation-oriented coverage metrics where we're trying to verify, did we fill the FIFO or did we trigger an assertion? And that's an area right now where Mentor and I suspect others are actually doing research to combine formal and functional techniques to be able to automate that process as well. But we are moving from the outside in to cover all of these. And what we're doing is we're combining the formal techniques and the simulation techniques, so we're actually using them together to achieve these goals. In addition, the other trend that we're seeing is that the new Accelera standard, this was covered earlier today as well, is emerging where we're using all different types of sources from simulation to emulation to feed into the common database to be able to support common tools for your metrics, for your verification, not only for coverage, but for code stability and for bug rates and others. In the area of low power, there's lots of different areas for verifying power, all the way from just verifying that your design turns on correctly and turns off to full system hardware, software for power control, and everything in between. This is a trend that we're also seeing where more and more people are now prioritizing power, even that trade-off between power and performance. Power has arrived as equally important. From the research group that shows the different levels of power management that people are applying in the design and verification process, 67% of the industry has made low power verification a priority. So in terms of technology verification enablers, as I run down to my last 5 minutes, there are 3 things that today I'd like to give you a very broad brush: intelligent test bench automation, multi-engine verification platforms, and application-specific formal verification. So the discussion was made earlier today, or the point was made earlier about is graph-based testing directed testing, and it is not directed testing. You've probably seen slides similar to this that show directed testing as we achieve coverage slowly in the red. Constrained random, that lets us start earlier, but then statistically starts to repeat and generate a redundant stimulus. And what the graph-based technology allows us to do is to start at the same ramp as constrained random, but to not slow down and to not repeat or to not produce redundant stimulus unless you want redundant stimulus, because you can do both and combine them, and I'll show you how right here. So here's a traditional SystemVerilog stimulus description on the left-hand side, coverage model on the right-hand side. So if you take a look at this, can you tell me, do you know if your stimulus description is matching your coverage model? You get 5 seconds. Right, so I mean, we're declaring our address field size, burst length, read and write, describing constraints, setting up cover group, cover point. So it's complex, and this is actually a very trivial example. This is what we see over and over again. that the stimulus description that was just created on the left-hand side, it's some large description of functionality, a test space, but the coverage model is overlapping, but it's not consistent. So this is one of the reasons with our intelligent test bench automation we're seeing such dramatic results, because all of the tests that you're generating in this area here, in the blue area, are generating tests you don't care about. At least you said you didn't care about, because it's not part of your coverage model. But you've got a significant part of your coverage model here over on the right-hand side that's outside your stimulus description. You'll never get there. That's one of the reasons that you don't get to 100% coverage. So one of the things that intelligent test bench automation can do is just make this whole process simpler. Right, so this graph here in the middle, this graph describes the exact same stimulus space that we just saw in the past two slides ago with the SystemVerilog constraints. It's the exact same thing. In fact, there's even a constraint embedded inside, right? So we've got 32 bits of address with 4 billion values. We've got a read and write operation, burst length and burst size, although there's a constraint that doesn't allow us to combine or cross all different combinations of size or length. This is exactly what we just described, except you can look at this in the graph in a picture and you can see this, see how it works. Well, what we can do with the coverage model is we can lay the coverage model right on top of the graph. So you ask, does intelligent test bench automation make random selections? It can, if you wanted to. So here what we've said is just let the 32 bits of address generate randomly. I don't care. Maybe at some point in time later I will care, and I'll create some coverage bins so that I get low, medium, high, or 10 different coverage bins across. But let's just say I run it randomly. I can set a cover point with a green box around my operation, and then I can put a blue box around my burst length and size and say cross all legal combinations, but make sure you pay attention to any constraints. So I've just created the exact same thing, but I've done it in about a third of the lines of code. I've done it in a graphical format so you can look at it and it makes sense. And I'm using a combination of systematic coverage-driven targeting as well as random, don't care, just let it run. If I want to do the same thing as random testing, I can just remove this box and remove that box and let the whole thing run randomly. And I'm doing the exact same thing as constrained random testing is doing. So it's no more constrained, it's no less constrained. It's the same exact test space. Except now what I get is I get this. I get a coverage model that I know is consistent with my stimulus description. Now you say, well, if I run this, I'm going to get the coverage fast and then I'm done, and I want to run more tests. Well, that's fine. Expand your coverage model. You say, oh, well, but I still think you're under constrained. Well, that's fine. Expand your stimulus model. It's all graphical. It's all easy to see. It's very much under control. So that's something that we're seeing take off right now. We have over 40 customers that have our graph-based verification, and they're averaging 40 times throughput. Some are only getting 10x. One customer got 170 times faster and got that 21% coverage that they weren't able to get before because their stimulus model didn't match their coverage model. And you probably don't even know it. So multi-engine verification platforms, we're seeing use across not only verification, RTL simulation, but hardware emulation and FPGA prototyping. But what's interesting to see is that there is some design size dependency here. Hardware acceleration and emulation tends to grow in usage as you get the larger design size. FPGA prototyping sort of falls off. Maybe once you get larger than what can fit inside a single FPGA, the partitioning and the process becomes too complicated. We saw this a little bit earlier today. Mentor is also working on unifying and integrating its verification environments across the entire process, starting from simulation through emulation and including software debug. So here's just one example. The debugging environment that we use between the simulation and the emulation today are exactly the same. It's like instant replay in an athletic event where we're able to capture the results from simulation or emulation, play them back, look at both hardware and software domains, synchronize, look at memory maps, physical virtual memory registers, variables, and values. In addition to that, we've also got a native software IDE that's consistent all the way from virtual prototyping through emulation, through FPGA prototyping, and even to post-silicon. So we do see this entire process all the way from the virtual prototype to the post-silicon coming together as well, as we saw earlier today. And then finally, in formal verification, what we're seeing is it's not just for experts anymore. And we're really leveraging this formal technology and, as I said, combining it in some ways very simple, just ways of being able to look at your design using formal technology and tell you what code or code coverage is unreachable for whatever reason, either dead code or just functionality that you're not using. And contrary to popular opinion, formal verification usage is actually increasing as design size increases, not the other way around. So here are some areas where we're applying formal in an application-specific way, making it push button so that it's more easy to adopt. So verifying FSMs, interconnectivity, we talked about that a little bit earlier, identifying X propagation and RTL issues, as well as, again, improving simulation coverage by identifying simulation code. And one of the earlier areas of application-specific formal verification, which is combining formal and functional technology for verifying clock domain crossings, which is a good thing because as designs are getting larger, we're seeing 9, 10, 11 clock domains on some of these larger designs. So some trends and some enablers in an SoC world. Really, where can you learn more? So here's where I go first is to verificationacademy.com. There are over 15,000 members registered now. You can see online courses and things like intelligent test benches or CDC or assertion-based verification. It's been very, very popular because it's really not a tool sell. It's really about technology and methodology. In addition to that, we also recently, you may have seen our UVM cookbook. In the past, we've recently announced our coverage cookbook, which is now available as well. So thanks for your time, and thanks for listening to me speak. Thanks, Mike.
Thank you very much. Do we have any questions from the audience at all? We have some time. One right, let's start front, and then I'll come to the back.
Yeah. Hi, Mark. I'm Saina from NXP. Okay. I'm Saina from NXP. In one of your slides, you mentioned that the effort towards the design is reducing and verification is increasing. What is the primary reason for it? Because we know the designs are also becoming larger. So,
I'm sorry, I didn't quite understand the question. Did you?
Yeah. Yeah, in one of the slides, you mentioned that the effort towards the design is decreasing, whereas the verification effort is increasing.
Front-end design is decreasing.
Yeah.
Well, as a percentage.
Yes.
As a percentage. So, yeah. So if that's most likely attributable to, again, if you look at the survey, you'll see more on IP, and the use of the reuse of design IP is continuing to increase. So Harry's survey will show that more and more of a design content is actually coming from reusing existing IP, either third party or internal. So that's one of the reasons that as a percentage of time, the amount of time that a designer is spending designing is going down compared to the amount of time a designer spent verifying.
Thanks.
Yeah.
Well, 2 more questions at the back, and then we'll move on to the next speaker.
Thanks.
Hey, this is Sukrut here. The graph-based specification which you mentioned, right, that works on specifying the input stimulus and also basically giving an idea of what of that should be covered using functional coverage, right? But normally in verification, what we see is that the functional coverage is heavily on the output side, or where you end up covering some states in the scoreboard or in the design. So does this help in kind of automating the coverage of those as well?
So actually, when we talk to customers, the vast majority of them tell us not that the input states or output states are the most important part. They say that they're all reasonably equally weighted. So they're interested in the controllable input stimulus space. They're also interested in internal and also external. In terms of the external state, the graphs can be reactive. So the graphs can actually be, they can actually observe the state of the design and make decisions based on what's happening at the state. So that can, the external states, even on the output, can be part of your coverage model. It's the input states that are the challenging part because the graph doesn't have direct control over them. However, what we're seeing is while on the external, on the input and output coverage, we're seeing 10 to 40x type of benefit. On the internal state coverage, we still see 20% benefit compared to constrained random testing. Now, it's not targeted, right? So the question was asked earlier, I think, by you about when we actually see some coverage holes, can you actually target it? In the graph-based technology, after every sequence is generated, it looks at what coverage isn't achieved and actually targets something for input or for output. For the internal state coverage, just like random testing would run, but it just tends to get higher coverage faster because instead of a bell curve of random distribution, it's not quite flat, but it's an almost flat distribution.
Hi, Mark. I'm Ashutosh. It's more an entrepreneurial question rather than a verification question. Where did you pull those graphs from? From the startups or your clients?
The graphs, meaning the charts with the data?
Yes, data.
Yeah, so those are actually, the honest answer is we don't know the companies that actually responded because it was a double-blind survey. So we commissioned Wilson Research to do the work, and they were not to tell any customers that Mentor was paying for the survey, but they also weren't allowed to tell us the names of the customers. So what they've told us is that there are, again, sort of between 500 to 1,000 customers around the world that range from large companies to small companies, include designers, include FPGAs, and in the survey, if you attend the session in April, or if you go to Verification Academy and look for Harry's blog, Harry will be blogging on the survey, and the first part of the survey answers your question as best as we're able, which is how many customers, how many respondents were silicon, how many were systems, how many were FPGAs, how many were ASICs, how many were custom, so that you can find out more information. But it's pretty broadly distributed. It's not just small companies.
Okay, thank you. Thank you for the questions, and we'll stop there. Thank you very much to Mark for his presentation. Thank you.